Find the scalar projection and vector projection of b, the vector 1, 1, 2, onto the vector a, negative 2, 3, 1. All right, we'll need to compute a couple of quantities first, the length of a and the dot product of a and b. First, the length. We know using our distance formula in 3 dimensions that we can sum the squares of our 3 components, then take the square root, and we will find the square root of 14 to be the length of a. Then for the dot product of a and b, we will take our products and sum in the usual manner, and we'll wind up with 3 for the dot product. Okay, so we're going to use these 2 quantities because, to begin with, our scalar projection of b onto a is given as the dot product over the length of a. So we can simply substitute in, and we find 3 over square root 14 to be the scalar projection. All right, so to remind ourselves what a scalar projection is, let's look a little bit at the graph. Now remember that a scalar has no direction. It is simply a magnitude. And indeed, in this case, our scalar projection is simply the length of the, sometimes we say, the shadow that vector b makes on vector a. And indeed, you can imagine the sun beating down from straight above. And we can see that what we have here is the length that b is traveling in the direction of a. Onward, we are going to compute the vector projection of b onto a. And this is going to be the scalar projection times the unit vector in the direction of a. And what we want here is we want the direction of a, but not its magnitude. That's why we're multiplying times the unit vector. Okay, so we have our scalar projection times our unit vector in the direction of a. And as we expect, when we multiply a scalar times a vector, our answer will be a vector. And it will be the vector negative 3/7, 9/14, 3/14. Now let's get a look at that vector projection. And you can see